Thank you. Good morning, everyone. So yeah, as mentioned, this is a joint work with Ahmad Ghazal from Huawei, and the topic will be BigBench. So basically, we work on some extension in direction streaming on top of BigBench. Here, just to give an overview about my talk. So I'll give I guess most of you are familiar with BigBench, but I'll just spend some time to remind you. So the main property, so it's end-to-end application level big data benchmark. It was inspired by the TPC-DC benchmark, and a lot from the schema and the tables were taken, and also 11 from the queries. However, since it's a big data benchmark, additionally were added the unstructured data, the reviews. This part here, and then also the semi-structured data, basically to represent a variety of data. And then the benchmark consists of 30 queries. As I mentioned, 11 were from TPC-DS, and the others were a new one representing analytical workloads. Later it was adopted by the TPC, I think around 2016. It was adopted as a TPC XBB standard, and there is also implementation in HiveQuell, Spark SQL, and Spark ML available. So then last year we presented the paper where we tried to address some of the limitations. So we tried to get away from the TPC-DS schema, and basically we simplified from more than 20 tables to around 5. And then also we introduced the late binding concept, which basically means we execute queries directly, querying the semi-structured data. And in the original BigBench, the semi-structured data was kind of presented still in a tabular form. And this was another thing we addressed basically in the data generator that we implemented. We introduced key value web blocks in JSON format, which basically you can directly then query. Then we replaced the 11 TPC-DS queries with another new one, focusing mostly on the semi-structured web blocks. So, however, there were still things that were not addressed, and as you can guess, that was the velocity, or basically the streaming part. So there is something in BigBench which is has a name, concurrency streaming, I think, in the title, but that's basically targeting more or less the parallel execution of queries. And to motivate further, so we see more and more application in industry which are targeting streaming and also around these main engines, and particularly here we see also functionality extending these new engines with Stream SQL and other analytical functionalities. And then at the same time, there are also multiple benchmarks, so micro benchmark and some application benchmarks. But then the micro benchmarks, they focus on a single operation, and the other application benchmarks, they also focus kind of tightly on particular use cases. So the idea is that we basically further extend BigBench, and we kind of provide a benchmark where the integration of storage, batch, and stream processing are together, and basically you can get them and execute all of them or part of them. So before I start, let me put also the requirements that we kind of defined before going into the implementation and thinking how to do this. So we wanted to have a configurable data stream so that we can cover multiple application scenarios. So this means from real time, which is usually in the second, in the seconds area, also to like batch streaming, where you can have even like hours of data which is aggregated and then also moved and processed. Then the other important thing was for the benchmark to be deterministic, because it Otherwise, it's very hard to basically compare and also validate the results. So that's why the important thing was to come up with a way to generate a deterministic stream, so that after this we can validate and verify the result that we got from the execution engines. And another important thing was to isolate the stream processing execution from the other elements. So for example, typically we have other things happening in parallel, like the stream generation. Yeah, so that was something also that we addressed. And last but not least, for us it was important to preserve the existing BigBench specification, also the architecture, the workflow, the execution, and the metric. So we did not want it to change anything. So what was our approach? So then we basically thought about the semi-structured data and the webhooks, which basically represent users going to a particular page and clicking and seeing things, and then these things are logged. And then at some point we have also web sales, which means that certain products are bought, and these things together, they are generated in a session manner. And basically what we saw is that we also have a timestamp, and what we can do is basically we take them and kind of sort them, and by doing this we can have like a time ordered stream of data. So that was kind of the general idea, and then the question was, okay, so now we kind of have a simulated stream, but then how do we define the streams? And so we came up with two types of streams, fixed window streams and then sliding window. So let me start with the fixed window. So on the y-axis you can see here these are different basically product pages, and on the x-axis these dots here, so this is the time, and then the dots represent basically people going and checking these pages and then generating in this way logs, so in JSON format. So what we said, okay, we can basically define a window size, and then based on this window size we can then divide the data in these separate windows. And then in the same way we define the sliding, or also called hopping window. In this case we have something called swipe, which basically defines what's the overlapping between the windows. And what does it mean in terms of data? It means that data is represented in two windows. For example, here between T1 and T2, the data that's here is in window 1 and at the same time in window 2. And we, of course, these need to be configurable parameters. So basically, the window size, the window swipe, and also the total execution time, we take them as input parameters for the generation of the data stream. And then this is kind of the architecture, the design overview that we came up. So first on the left you can see this is the original BigBench architecture, which is quite simple compared to this thing here. So let me first explain the original architecture. So we had usual data generator, we have a persistent storage layer, and then batch processing layer, and usually this was HDFS, the data was generated, stored, and then read here, processed, and the result written back again. So in our case, we followed this approach, but basically in order to produce the stream, we introduced three new components: the stream generator, fast access layer, and stream processing component. And as you can see, the data and the stream generator can be combined. So these are all technology agnostic components here that I described, and later I'll show also implementation. So yeah, then we have this fast access layer, which can be seen as an intermediate buffer, and then we have the batch and the stream processing, which can be also implemented in one component. And then in addition to that, we have we define two modes: active mode and passive mode. And the reason for this, again, to target the different types of streaming that we have, and also to make sure that our stream is deterministic and not influenced by any other factors. Yeah, so here just to explain very fast active and passive mode. So the main difference is that in active mode we have a parallel execution, which means that the stream generator and the actual stream processing happen at the same time. So basically here we generate the stream, we push it to the fast access layer, and then the stream processing component takes the data from there, processes it, and then writes the result to the persistent storage layer. In the passive mode, we have a sequential execution. This means that all the data and the stream preparation is done in advance. Then it's stored on the persistent layer. Then it's pushed here into something which we, let's say, call buffer, which can be in-memory buffer, but can be also something else. And then from there, basically the stream processing component reads the data, processes, and again writes the persistently the result. So this is basically the difference. Then about the workloads, so we identify 4. So in general, we have currently 5 queries which we executed. 4 of these queries were basically picked from the existing 30 queries that we already had, and all of these 4 queries were suitable to be executed on windows of stream data. And we added another one which basically represents a very simple case of pattern detection. And yeah, basically you see here this time, which is it's for the sake of the example in the paper is 120, but of course that's a configurable number. Yeah, so this was the workload. And in terms of metric, we defined 2 metrics: execution time, which is the basically the processing time execution. So from where we start the query execution to the moment it ends. And then we have also something else called end-to-end streaming execution time, which is basically including it's from the moment when the data stream was generated until the moment where the execution of this window of data is finished, and then we are ready to write it. Another important thing was the validation. So how we do the validation? So the idea is to be similar to the current BigBench, where we have a validation based on a particular scale factor. So the idea is that we can basically store each result of a query execution persistently, and then once we have finished the benchmark run, we can then go back and compare this single executions against the golden result, and by doing this we can make sure that our execution is valid and verified. And we did then a proof of concept, so basically a very fast implementation. Here I show you how we implemented the 2 modes. So we use Spark for the stream generator, HDFS for the persistent storage layer, and then for the fast access layer in the active mode we use Kafka. So in this case you can see here all the details. So basically the stream generator was the producer. He generated data, pushes it to Kafka, and then the processing module, in this case Spark streaming, was the consumer and takes the data and processes it and writes back the result into HDFS. And basically this is more or less the main difference. In the passive mode, where we don't have direct connection, basically we generated the data, store it here, then we push it in memory buffer, and then from there on the Spark streaming was able to fetch the windows and execute them. And for this we can use other things like in-memory HDFS and so on. Okay, so to conclude, so in this paper, it's a work in progress. We propose a streaming extension of a BigBench, and we propose the configurable active and passive modes, which basically kind of try to cover the possible streaming requirements. And we introduce fixed and sliding window streaming semantics. And this is basically an overview of the features of these 2 modes. And of course, that's just the beginning, and there are many more things that we need to cover, and they are not yet there, or problems that just appear. So one thing will be to basically re-implement the whole thing in Spark structure streaming, as the Spark streaming is more or less not that expressive and will be replaced by it. Another thing is to come up with new implementation in Flink and Samza, and also now they also support SQL, so that's exactly the target. In terms of workloads, of course, these 5 are not covering all the possible cases, and then we need new ones which are more complex and even go in direction of machine learning. Then we also need support like for swiping window in active mode, which is a bit harder, and then things like out of order records processing, so how this will be handled, that's also quite interesting. The parallel query execution can be easily added, yeah, and then of course large scale validation. And thank you.
We have time for 1 or 2 quick questions.
So maybe one question.
Yeah.
Did you actually try, or I saw you had some numbers?
Yes. Yeah, I didn't put them here because of the time and also because it's a work in progress. So yeah, we had some things, but we did not really. I mean, we have the results, so things are running, but we are not happy with the details. That's why we think about structure streaming. I think it will be a better choice.
Yeah. So maybe 2 comments here for your architecture.
Yeah.
So if you use Kafka, that will usually be upon
Yes.
this. So you can basically try to directly connect your streaming source to Spark Streaming or Spark Structures.
That's actually what's here.
Okay, and in this case, basically, because you can always, like, you can have open or closed word assumptions, or you can have Spark control the latency of the incoming tuples, or you can basically say the buffer, like you use event times for the latency. So do you handle this? Like, do you make a distinction between processing and event time?
I mean, yeah, we have these things, and that's in this execution, in the end-to-end execution, but we haven't really experimented there. And also, yeah, so I think also still the architecture can be, it's not fixed. I think it allows to play a bit with which part where should run. So, yeah.
Okay, thanks.
Thanks a lot.